My goal in this video is to define the derivative of a vector valued function. So I have some things to fill in here. But what I actually want you to do first is to just look at what I've written down here. I have a vector valued function. In fact, it's our helix. And I want you to take a derivative. I haven't defined it. I haven't shown you an example. Trust yourself. Do something that makes sense and take the derivative of that vector function. Okay, I'm hoping what you did to take the derivative of this vector function is that you took the derivative of each of the scalar component functions. Thinking about what we've seen so far, that the calculus on a vector function is simply doing the calculus on the three scalar component functions. If that's what you did, then you already know how to take the derivative of a vector function. Now we just need a definition of derivative that says that's what we should do. So I want to write down the formal definition of derivative that looks a lot like the definition of derivative from Calc 1, and then we're going to make sure that this is what it really says to do. So I need to take a limit as delta t approaches 0. Right in Calc 1, we probably called that h, or delta x. I'm going to call it delta t because I'm using h as one of my scalar functions. And then it should be r of t plus delta t minus r of t all over delta t. This should give me the derivative, right? This limit statement's my definition, and of course I need to write provided the limit exists. Well, I need to justify that this limit statement, when it exists, says take the derivative of all three components. So I want to start off by looking at this difference quotient. So let's imagine we have a curve in space, and I want to look at what r of t means, what r of t plus delta t means, and what happens when I subtract those two vectors. So let's just imagine we have some curve in space. It doesn't need to be the helix that I'm using as an example on the other board. R of t, for every value of t, points to a point on that curve from the origin, r of t. R of t plus delta t, well, that should just point at a different point. And so I have two vectors pointing, both with initial point of the origin, both pointing to some point on that curve. And now I need to think about the difference between r of t plus delta t and r of t. Well, I could think about my parallelogram law, right? And the parallelogram law says that this difference should point from the terminal point of this vector to the terminal point of that vector. So that's my difference vector. Okay, so now in thinking about the difference quotient, I'm supposed to take that vector and divide it by delta t. Well, what I'm really doing is dividing by a constant, right? And so that's really just changing the size of my vector. So depending on how large you want delta t to be or how small you want delta t to be, it's just changing the size of that vector. So I'm going to let that darker blue vector represent this construction, just a vector. And now our job is to take a limit as delta t approaches 0. Well, as delta t goes to 0, my vector is going to resize itself. But what happens to the two vectors on top? Well, these 2 points get closer and closer and closer to each other. And so I could imagine that at some point my vector might look like that and then look like that. And when this limit exists, I get a vector that looks like it just touches the curve in one point. I get a vector that's just tangent to my curve. And so this does seem like a good definition of derivative. In fact, it looks like it's telling me about a vector that's tangent to my curve, just like the derivative in first calculus talks to us about tangent lines. Okay, so that's what those vectors mean. Now let's make sure that that definition says that we get to just take the first derivative of each of the component vectors. Thinking about how limits of vector functions work, well, this is a vector function itself, right? It's the difference of two vector functions over a scalar. And so when I evaluate this limit, what I can remember is that means I just take the limit of all three scalar components. And so here, I'll replace this with f of t plus delta t, comma, g of t plus delta t, comma, h of t plus delta t, and then minus r of t itself. I'm using my angle brackets here just out of convenience. Running out of room here at the edge of the board. So let's see if I can fit that in there. Minus f of t, g of t, h of t. All divided by delta t. Okay, well now inside of this limit, I could imagine just doing the vector subtraction. F of t plus delta t minus f of t. Is the I component of that difference vector. And then g of t plus delta t minus g of t. There's my j component of that difference vector. And then finally, h of t plus delta t. Still divided by delta t. Well, what I can do now is use scalar multiplication and divide each component by delta t. And I see what's going to happen in all three slots in this vector. The definition of limit for vector functions now says take the limit of all three of these scalar functions. Well, as delta t goes to 0, this is the difference quotient of the function f, so that's df dt. This is the difference quotient of the function g, delta t is going to 0, that's dg dt. And so literally this is just a definition that says take the derivative of all three scalar functions. So I could come back to my definition here, and I could write that this is equal to df dti plus dg dtj plus dh dtk. And instead of saying provide the limit exists, that's certainly true, I could say provided those three derivatives exist. So, to take derivatives of vector functions, all we have to do is take derivatives of the three scalar component functions.